What's going on in the North Atlantic right now?
Yeah.
We've got meltwater. Okay. What the prior data indicates is that a massive influx of meltwater is because you're adding all this fresh water, you are decreasing the surface density, you're making it unlikely for the water to sink. And if that happens, the whole thermal haline flow slows or stops. So the main driver in all of this is salinity, basically affected by a huge amount of meltwater. So what's happening right now? Greenland is melting away. We have a huge amount of meltwater. And we need to also look at what's going on in the Arctic Ocean, specifically the Beaufort Gyre. The Beaufort Gyre is a clockwise flow,
Hmm.
which is affected by the Arctic dipole. And the Arctic dipole, actually, when we first discovered it, we understood it to be a mechanism that determines whether or not sea ice stays circulating, floating around within the Arctic Ocean basin or gets pushed out through the Fram. Well, thanks to a recent research by my good friend Igor Polyakov, who is looked at how the Arctic dipole is impacting the halocline in the Arctic Ocean, which then impacts the Beaufort Gyre. The Beaufort Gyre could also, and this is the interesting bit, it's a clockwise gyre, which means that the flow domes up in the middle. You have a convergence zone in the middle, and you've
Oh.
got riverine water input. So you have a doming of basically fresh water
Yeah.
in the Baltic Gyra, and conditions are could happen that that fresh water goes right out through Fram and adds it to the North Atlantic. You have all these riverine inputs from the Eurasian side, the North American side. This fresh water is getting entrained. And unless you have ventilation mechanisms or
Mm.
Ekman pumping to remove that vertically within the Arctic Ocean vertical structure,
Yeah.
that can build up and get moved out. And this is where the role of the Arctic dipole impacting the halocline comes into play.
Wow.
So the main point of all of this is that it's a freshwater buildup. If you look at now, there are other factors to look at. You can look at what's the North Atlantic Oscillation doing, what's the Arctic Oscillation doing. The position of those high and low systems and how they move, which way the air flows, what the temperature changes and precipitation change patterns across Europe and so on. That all plays into a role, as does the Atlantic Multidecadal Oscillation, the AMO, which impacts sea surface temperature. All those are factors. We also need to look at what's called known as double diffusive mechanisms. When you have water that contains, salt, it's not just temperatures that mix, but the salinities that mix.
Right.
As it turns out, the salinity mixes at a higher rate than does the temperature mixes, than does the heat fluxes,
Okay.
and that can drive things in a certain way. A good example to look at this is what happens when sea ice forms, and you actually see the video of the brine rejection, which is the heavy salty water, and you just see going just
It goes
big plumes just going
right.
down.
This is
So
serious.
the salt mixes at a higher rate than does the temperature differences. So you have to look at that as well. And research is now showing that the role of mesoscale eddies is extremely important in grabbing the atmospheric heat and the CO2
Mm-hmm.
and entraining it into the ocean. Basically, it's the go-between.
Right.
It's what facilitates the mixing between oceans and atmosphere, and it's part of the
Wow.
reason, as we're now
That's
understanding,
big
why
stuff.
the oceans have absorbed 93% of greenhouse gas energy emissions over the last 50 plus years or so.
Wow,
That
Jim.
that's what's going on. So there are certain folks, the atmospheric folks, who are pushing the notion that aerosols are driving AMOC. Sorry, that is just simply incorrect. Now, I am not here to say that aerosols are not a factor. They are, with concern to the atmosphere.
Mm-hmm.
Okay,
Mm-hmm.
look at the work that Guy McPherson has done. Look at the videos he has posted. Okay, he, you know, has stated very well that the removal of sulfur can cause a warming. Now, the warming is, depending where you look at, but the general consensus is that the removal of the sulfur can cause a warming of about zero point 0.4 C in the
In
atmosphere.
okay.
Now, to say that, okay, you remove the aerosol, now the sea surface temperature is going to increase by 5 to 7 C when the atmosphere is increasing by zero point 0.4 and air has a far lesser specific heat than does water. I'm sorry, the physics just doesn't bear that out. Now, you can say, well, you're letting heat energy get through. Okay, fine. Um, Heat energy, when the light penetrates the ocean, okay, it depends where you're at. Some people say,
Okay.
well, light can penetrate down to 200 meters if you're on the equator.
Oh
And,
yeah.
and there's not much happening there. There's
Right.
no productivity. There's no phytoplankton to do with it. Yeah, so you can see down to 200 meters. Us oceanographers, when we do a lot of things like, oh, let's calculate the total productivity for the water column, we typically take 100 meters. Integrate from 0 to 100.
Okay.
We typically do that, but light penetration, actual heat energy, is typically, you can may see down to 100 meters, but the energy is most felt within the first, 5, 10, 15 meters, something
Really.
like that. And when you get into the North Atlantic, which can be very turbulent, you, you're lucky if it's 1 or 2 meters down,
How many?
and also 1 or 2. I
Mm.
mean, and also light energy, it attenuates very rapidly through the water column. In fact, it's a exponential decay function. So most of that heat is going to be absorbed right in the upper few meters. S- Uh, the initial absorption. It's now other physical mechanisms that then take that heat and then train it down to 700 meters. So to say that the aerosol is driving the AMOC is just simply incorrect. I'm going to argue myself blue in the face with atmospheric folks about that. But here's the other thing that a lot of them don't take into account.
Okay.
You have phytoplankton that, wait for it, release dimethyl sulfide, DMS.
Ooh.
And as I talked about in my last video, we have sea ice algae can also release sulfur. So you're still going to have some sulfur in the
Yeah.
atmosphere.
Yeah. It's a confluence.
Now, whether that neutralizes the reduction in the sulfur from burning the fossil fuels, that remains to be seen. But still, it's an offset. So to me, that's further evidence that this notion of aerosols driving AMOC is poppycock. See, the data simply
Mm.
doesn't bear it out.
Right.
There's no controversy at all. I
Good.
actually spent this weekend um, looking at about 8 or 9 peer-reviewed papers that looked at aerosol and AMOC, and they were very lengthy, very detailed.
I saw a
And the
couple.
consensus, looking at the papers, is there is no consensus.
Oh.
Some papers said, "Oh yeah, there's an effect." Other papers were saying, "We've getting contradictory results here." Other papers are saying, "No, that it doesn't do diddly squat." So, and some tried to do some regression analysis where, if you have a bunch of variables,
Mm-hmm.
what percentage does each variable contribute to the observed impacts on the
Right.
dependent variable? It was kind of all over the place. It was nothing that was like, oh, this is over 50% of the variation. So again, aerosol masking effect impacts more the atmosphere than it does the ocean. That's my take on it. Looking at the papers, knowing from my as an oceanographer and looking at the oceanography research and just, well, I don't know, basic thermodynamics and physics,
Okay.
the main driver is changes in the salinity, changes in the density. If I was to be generous, that okay, removal of aerosol is ancillary, but it's not a driver, not a main driver. That's my main argument.